This is Mrs. Fraser. In this video, we are going to be learning about arithmetic sequences. So sequences are just functions, and arithmetic sequences are linear functions. So we should already be very familiar with these. If we can determine a pattern, we can write a formula for it. See if you can determine the patterns below. Okay, so when we're determining patterns in arithmetic sequences, what's really important, first of all, is our first number. So when I look at this pattern, we can see I start with 11. And each time I'm adding 2. And the next one, we can see that I'm starting with 5. And each time I'm not adding, but I'm multiplying by 3. And in the last sequence, I'm starting with 1. And I keep the same term. So I have 1 again. And then to get my next term after that, I'm adding the 2 previous terms. 1 plus 1 is 2. Or to get to 3, 1 plus 2 is 3. Or to get to 5, we have 3 plus 2 is 5. So we start with 1, then add 2 previous terms. So what I'm telling you is all of these are sequences, but not all of them are arithmetic sequences. So we're going to look at what makes an arithmetic sequence. And I'll tell you that this one is our arithmetic sequence. So this one will be a linear relationship, while the other two may be sequences and also functions. They are not arithmetic. So let's look at some important vocabulary. Term. In a sequence, a term refers to each number in the sequence. For example, in sequence 11, 13, 15, 7, the first term is 11. And the fourth term, 1, 2, 3, 4, is 17. We also have what is called notation. So we can refer to the first term as A1. This is known as a subscript notation. So we would say A1 equals 11. But we can also refer to the first term as f of 1. This is known as function notation, which we are already familiar with. So f of 1 equals 11. So this already looks very familiar with us, where 1 is acting as my x value and 11 is acting as my output. So my input is 1, my output is 11. My first term and what my first term actually is, the output of that first term. So let's fill in the chart to identify the terms using both types of notation. Okay, so term number 1 is 11, and then I have term number 2 is 13, term number 3 is 15, term number 4 is 17, and since I know that each time I'm adding 2, then my fifth term will be 19, and my sixth term will be 21, because each time I'm adding 2. So in subscript notation, I would have term 1, A1, A2, A3, A4, A5, A6. And function notation, I had to have f of 1, f of 2, f of 3, f of 4, f of 5, and f of 6. So here's a question. What do you think a subscript n refers to? So a subscript n refers to what we call the nth term. So to determine like any term. So it's like an unknown term. It's kind of like when we use x and y, where we're not giving a specific value, but we're saying what could be used to determine any term. So say I want to know the 100th term, I would just use nth term, so any term. So let's look at a little bit more vocabulary. Arithmetic sequence. So we talked about how only one of the above was an arithmetic sequence. Well, an arithmetic sequence is a sequence whose term changes by adding the same number each time. This might sound familiar to you. We've already dealt with something that adds the same thing each time, and we call that something our rate of change. So this is like my linear relationship. So in a linear relationship, I always have a constant rate of change. That constant rate of change is called my slope. And an arithmetic sequence, which is also a linear relationship, we are replacing what we call as a slope as a common difference. The reason why we call it the common difference, it is the number that is added to produce each term in an arithmetic sequence. It can be found by subtracting the second number minus the first number. So let's back up just a little bit. So for example, to find my common difference of 2 here, I could just do 13 minus 11, which equals 2. So 2 would be my common difference because I add 2 to get to 13. But it's called the difference because I can subtract to find it. So what is the common difference for our sequence? Well, the common difference was 2. So don't make the mistake of reading difference and thinking that this would be negative. Sometimes it's negative, but sometimes it's positive, just like slope is sometimes positive and sometimes negative. So which formulas can produce our sequence? So keep in mind that when we're dealing with linear relationships, we have y equals mx plus b, where m is my slope and b is my y-intercept, which is when x equals 0. Well, arithmetic sequence are not entirely different. I'm still looking for something that has that rate of change, and in this case, we're talking about my common difference. So I need something where I'm taking and multiplying by 2. But in this case, I'm multiplying my my n, my term number. So remember, we use n to talk about our term number. Which is my input. Okay, so if I look at all my options here, they look a little different. So first of all, I have it written in 2 ways. We talked about those ways, backing up just one more time. We have it written in subscript notation. We have it written in function notation. So here in subscript notation, I have an 11 plus 2 times n minus 1. So I can see I'm multiplying by 2. So that might be an option. I have an equals 2n. I can see I'm multiplying by 2. That might be an option. And I have an equals n plus 2. Well, this isn't an option, because I'm not just going to add 2 one time. That's not going to happen. Like, for example, if I use 1, my first term, 1 plus 2 gives me 3. Well, if we go back to our table, my first term is not 3, it's 11. So that does not get me my actual value. So we're not just taking my term number and adding 2 to it. So that's not an option. Let's look at our function notation. So my function notation, I have 11 plus 2 times n minus 1, just like this first one. And I have 2n, just like the first one. And again, I'm going to eliminate this one because we already know that that's not an option. Okay, so this is where our slope-intercept form starts to differ from our arithmetic sequence form. So let's go back to our table to see if we can determine what kind of patterns we see. What's important in an arithmetic sequence is not my y-intercept, but it's my first term. And in this case, my first term is an 11. So I'm looking at how can I get to any term based off of this first term. So we're focusing on our common difference, what I'm growing by each time. So here I can see I'm growing by 2, and I've grown by 2 one time to get to 13. And to get to my third term, so let's just make a little mark here. I've multiplied by 2 one time to get to my second term. To get to my third term, I've multiplied by 2 two times. So now I've grown by 2 twice. And to get to my fourth term, I've multiplied by 2 three times. So to get to 17. So I'm starting with my previous term, 11, and I'm adding 2, but I add it only one time to get to 13. But to get from 13 to 15, I'm starting with 11. Oops, sorry, let me erase that. I'm starting with 11, and I'm adding 2 two times to get to 15. And then to get to my fourth term of 17, I'm starting with 11, and again, I did that again. Sorry. I'm starting with 11, and I'm adding 2 three times, or I'm adding 6 to 4, 6 to get to 17. So what you can see is that each time I'm adding 1 less than the actual term number. To get to my second term, I'm adding it once. To get to my third term, I'm adding it 2 times. To get to my fourth term, I'm adding it 3 times. So this brings us to our formula that help us find any term that we need. So to find any term, I'm starting with my initial value of 11. I'm adding 2, but I'm adding it 1 less than the number of terms I have. So for instance, to get to my second term, I'm doing it 1 time. 2 minus 1. To get to my third term, I'm adding it 2 times. So 3 minus 1. To get to my fourth term, I'm adding it 3 times. To check to see if I'm right, I can see 11 plus 2 times my first term minus 1. So 11 plus, well, let's do what's inside the parentheses first. 1 minus 1 is 0. 2 times 0 is 0. 11 plus 0 equals 11. So my first term A1 or f of 1. Okay, so we plugged in our 1 value. My first term is 11, which is correct to my table. So it's slightly different where all I'm doing is this value, which was my y-intercept and y equals mx plus b, is now my first term. So these are both the same function for that. So how could this be used to find the 100th term of my sequence? Well, I start with 11, and I know I'm going to add 2. Well, I need to add 2 99 times. So I need to add it 100 minus 1 times. 100 minus 1 is 99. So 2 times 99 is 198 plus 11 equals 207. Did I do that right? Let's see. 200 and I'm sorry, 209. Okay, so let's start to make some connections. And I know that this video is getting rather long, but let's try to find the common differences of the sequences below to see if they are arithmetic. So my common difference, I have 2, 4, 8, and 16. So a common difference is something that I add each time. So first I'm adding 2, but then I'm adding 4, and then I'm adding 8. So there is no common difference because I'm not adding the same thing each time. So no, it's not arithmetic. Number 2, I'm adding 10 to get from 20 to 30, and 10 again, and 10 again. So the common difference is 10. Yes, it's arithmetic. And number 3, I'm taking away 2 each time. So my common difference is negative 2. And yes, it's arithmetic. So for the arithmetic sequences, can we determine the formula? Well, number 1, we can't. But number 2, I know that and let's use our function notation. So f of n, my first term is 20. And from that first term, I know I'm adding 10 each time. Now, thinking about how often I'm going to add 10, well, I'm adding 10 one time to get to my second term. So I kind of test this out. I know if I'm plugging in, I'm not going to just do 10 times 2 to get to my second term. But I'm going to have to actually do 10 times 2 minus 1. So I'm going to have 10 times my term number minus 1. So again, this is my initial value or my first term. And this is my common difference. Okay, and number 3, my common difference is negative 2. And my first term, so I have f of n. My first term is negative 3. And I'm going to add my common difference. Now this time, I don't really need to add it. I can say minus 2, because my common difference is negative 2, times n minus 1. So you should start to notice that n minus 1 will always be inside that parentheses for our arithmetic sequence formulas. So our formula for all arithmetic sequences would be f of n equals my common difference, d. Oh, I'm sorry. My first term. Let me erase that. My first term, f of 1, okay, plus d times my term number minus 1. Another way we can write that, if we're using our a1 or an equals my first term plus my common difference n minus 1. Okay, so let's match some of our arithmetic sequences with their formulas. So I can see number 4 here has a common difference of 1. Okay, so looking for a formula that has a common difference of 1. So that is like my slope, so it's what I'm multiplying by. So the only one that I see that has ones that I see that have a common difference of 1 is B and E. And then I'm always going to start with my initial value, which is my first term. So in this case, 4 goes with B. Number 5, I can see the common difference is negative 5. And my first term is 0. So looking for a common difference of negative 5, that's like my slope, what I'm multiplying by. The only one I see that I have that I'm multiplying by negative 5 is right here. And you can see that I don't see where my common or where my initial value is because my initial value is 0. So if I add 0, I'm just going to end up with the same. So in this case, my formula that matches is D, because that's like 0 minus 5 times n minus 1. Number 6, I can see that my common difference is plus 1. And my initial value, or my first term, is negative 5. So 1 is my common difference, or it's like my slope, my rate of change. I can see E has a common difference of 1 because 1 is always in front. And my initial value in E is also negative 5. So those match. 1, 7, 13, and 9. I can see my common difference is 6. So I need to either have A or C, but notice that here, this is a common difference of negative 6, so those won't go together. So it must be A, so I'm going to think, well, I can also just replace f of 1, okay, would be my first term. That's another way to write my first term. So 7 would go with A. And last, I can see negative 5 to negative 11 is going down 6 each time. So my common difference is negative 6. And my first term is negative 5. C. Okay, for number 9, 10, and 11, let's determine the 10th and 23rd term of each arithmetic sequence below. I'm going to do number 9 with you, and then I'm going to let you do number 10 and 11 on your own, but you can stop and check. So if I want the 10th term, so f of 10, I'm just going to plug in 10, just like when we are evaluating functions. are doing function notation. So f of 10 will just be my 10 minus 1, which is 9. So 2 times 9. Be sure you follow your orders of operations. So 2 times 9 is 18, plus 8. So 26 equals f of 10. So f of 23, this time I'm plugging in 23 for my n. So 23 minus 1 is 22. Two times 22 is 44. Add my 8. 52 will give me f of 23. So f of 23, or my 23rd term, would be 52. So there's lots of ways to check. I really could start with my initial value of 8, and I could add 2 every single time to get to 52. That's a possibility. And I can just build my table knowing that this is my first term, and I'm adding 2 every time. Same, that's a little bit more difficult to do than my 10th term, but my 10th term might be a little easier, so I could go ahead and know that my first term is 8, and I could add 2 until I get to my 10th term, which would give me 26. So those are ways that you can check those. So if you will pause the video, go ahead and try number 10 and 11 for yourself, and you can turn back on to check. Okay, so for number 10, the 10th term would be negative 92, and the 23rd term, negative 222. For number 11, the 10th term would be 36, and the 23rd term would be 75. You're welcome to pause and check further as you need. Moving on to our last page. It says, what type of graph do arithmetic sequences produce? So we're going to graph number 4 and number 5 to find out. Now, let's keep in mind, first of all, that I already told you that these are functions and that they're a lot like y equals mx plus b. And I think I actually already mentioned that they are linear. So now we're just going to prove that. My first term here, I know is 6. My second term is 7. My third, 8. And my fourth, 9. Now this is proof to you that this is just another way really to write our y equals mx plus b. We really could take any y equals mx plus b equation and write it as an arithmetic sequence. But instead, my function, or my y equals mx plus b formula, would look different because my y-intercept here would be 5, where in my arithmetic sequence, I use my initial value, or my first term, as 6. And number 5, I have 1 and 0. I have 2 and negative 5, 3 and negative 10, and 4 and negative 15. So again, a linear relationship. Again, I can back it up and I could see my y-intercept. But again, we would be focusing on our first term when we write it as a sequence rather than our y-intercept. So if you recall, if I look at the sequence formula, my sequence formula here was a common difference of 1. So I have f of n equals my common difference of 1. And my first term is 6. So I'd have 6 plus 1. I'm sorry, 6 plus n minus 1. No common difference is on the outside of the parentheses. And in number 5, my common difference is negative 5, and my first term is 0. So I'd have f of n equals, I don't need to write 0, so I would just, in this case, have negative 5 times n minus 1, which we already looked at both of these above. So if I compare these to my y equals mx plus b, and look at my y-intercept. I would have y equals my slope, which is the same as my common difference. So in this case, I just have x, because my slope is 1. And my y-intercept is 5. This is going to get me the same thing. 1 plus 5 is 6. And over here, again, my slope is -5, and my y-intercept is actually, let's see, I think it's 5. Let's make sure we're correct there. So I have -5x plus 5. So let's plug in, well, 1, -5 times 1 is -5, plus 5 is 0. So both of these work. We're just looking at another way to write our same function. Hopefully this video helped you understand arithmetic sequences. Make sure that you keep this sheet and put it in your notebook for future reference. Watch